Welcome back, everyone, to Planet Watch, the daily news show where we explore some of our greatest challenges and opportunities to addressing climate change. I'm your host, Kyle Farrell, and today our topic is global cooling. Now, I know here on the show we talk about the opposite almost every day, that being global warming. But a viewer recently sent our team a fantastic question that inspired this episode. He asked, how can we keep people, places, and things cold in a rapidly changing climate, all without making the world even warmer? Our team loved that question because it exposes the dichotomy of technology that provides us with comforts like frozen food, with other technological innovations we've created to close the hole in the ozone layer and to increase energy efficiency. When we stroll down the frozen aisle at the grocery store, it's difficult to really acknowledge the power it took to supply those foods with the proper conditions and temperatures all the way along the supply chain, from the factory to the store to your freezer at home. The same is true when we seek refuge from the summer heat by cranking down our home thermostats, or if we're out on the street by walking into a chilled coffee shop or office building. Air conditioning the world provides us with a fantastic quality of life in more ways than we can imagine, from food to medicines to public health and safety. But on this show, we know that the luxuries of consumption often conflict with what the world can handle and with the needs of generations to come. This week, we've done some research for you on what we've dubbed global cooling, the paradox that cooling our controlled environments contributes so heavily to climate change. Let's dive right in. In our research, we found that the most widespread and climate-impacting means of global cooling fall under these two umbrella categories: cities and buildings, the places we live and work, and shipping and warehousing, mostly of food and pharmaceuticals. And in today's episode, we'll be taking a look at all of them. By the end of the video, you'll understand how each cooling system works and how they contribute to climate change, along with any promising developments like technologies to reduce climate change in the cooling process. By current estimates, more than a third of the world's energy demand could be used for air conditioning in buildings and vehicles alone by 2050. A third. To contrast that staggering statistic, American households and businesses today use between 6 and 12% of all national electricity output on their AC. Remember, the rising middle class doesn't produce their own food in most cases either. Instead, middle-income households buy refrigerators and freezers to store food. More households and communities are also gaining better infrastructure and access to electricity grids every day, allowing them to install cooling and appliances that demand more energy. Based on current economic projections, we're talking about almost 1 billion new households by 2100 who will be customers of cooling systems. Their comfort and convenience matters just as much as anyone else's in the developing world, of course, but it's so important that we develop sustainable and ultimately clean ways to provide those households and businesses with cooling services as demand skyrockets. Before we discuss today's cooling strategies and the problems therein, we thought it would be eye-opening to highlight for you how people in the desert handled the heat in the past, before electricity, oil, or chemical coolants existed. Besides creating dense, shaded compounds with small windows for optimal shade, Middle Eastern architects used these three design and engineering strategies. The first is a rudimentary design to maximize airflow through an interior space. It's called direct wind entry, in which a tall tower captures wind that pass a few meters above the sand. And at the bottom of the tower sits a dust collection receptacle that collects any desert sediments that gravity has filtered out of the air. Although the wind entering from outdoors is relatively warm, it's better than nothing at all and works in tandem with the shade and cooling materials that keep people and food relatively chilled inside. Now, the wind-assisted temperature gradient gets more technical, creating a negative pressure zone to guide hot air into the ground, where underground water cools the air before it rises through interiors and out a vertical chimney. The solar chimney also takes advantage of the Coanda effect, or air pressure differentials, using thermal energy from the sun's rays to heat a chimney. In this case, though, that low pressure zone is at the end of the intended airflow path, but the physics checks out all the same. Without assistance by wind or water, the solar chimney draws hot air into the ground where it moves through a cool chamber. That airflow passes through the interior living or working space toward the heated solar chimney at the top, where it escapes as cool air. Those are just some of the brilliant ways that humans have controlled our internal environment in the past, clearly without the need for fossil fuel energy, nor even water in some cases. Later in today's episode, we'll explore the high-tech systems that cool the modern-day Middle East and compare them. So how do we take hot air and remove the heat and moisture from it in the modern day? There are a few chemicals involved, called coolants or refrigerants, that have truly changed the world. Some of the most notable, or should I say notorious, coolants are fluorinated gases, which have long nomenclatures like chlorofluorocarbon, or CFC for short. Fluorinated gases have an incredible capacity to hold heat, making them great at extracting heat from the air in our homes and appliances. But when they end up in the atmosphere, fluorinated gases trap heat even more effectively than the greenhouse gases we know and love, like carbon dioxide and methane. For decades, industrial and post-industrial regions relied on the gases called CFCs and HCFCs for cooling. These, in fact, presented yet another challenge to the climate. Not only did they trap heat, but by reacting with ozone molecules in the upper atmosphere, the chemicals depleted the world's solar blanket and allowed more solar heat to penetrate the atmosphere. Imagine that, heating up the planet among all the greenhouse gases already trapping heat up there, by breaking down the ozone layer. Once scientists proved that this was the case, almost every government took action to stop and even reverse the damages. The multilateral agreement was called the Montreal Protocol, and Kofi Annan, the former Secretary General of the UN, called it perhaps the single most successful international agreement to date. That was 1987, and Kofi Annan was right. The US had fully halted CFC production by 1995, and other countries were nearly as ambitious on average. But today, after studying and implementing alternative coolants, the ozone layer has effectively been restored. But wait, it would be such a relief if phasing out CFCs and HCFCs was the sole key we needed to unlock climate action. But then what do we use to cool our buildings and factories and refrigerators after the Montreal Protocol? Well, there were several options, including ammonium and propane, but the one that was most familiar at the time, and the easiest to scale up as a replacement for CFCs, was another fluorinated gas called hydrofluorocarbon, or HFC. HFCs today are used in even the most sustainable Energy Star appliances, and they don't deplete the ozone layer the way that their predecessors did. They do, however, have incredibly damaging greenhousing properties when incidentally released from the cartridges inside air conditioning systems. That unfortunately happens all the time, especially when people in factories dispose of outdated or broken refrigeration or AC systems and release the chemicals into the atmosphere. Just like in 1987, scientists came out with new studies indicating that HFCs hold heat in the atmosphere 1,000 times to 9,000 times more than CO2. And that, again, triggered hundreds of diplomats and leaders to gather and re-examine the solution that they had reached in Montreal back in 1987. That conference was held in 2016 in Kigali, Rwanda, and the countries present agreed to phase out HFCs just like they'd phased out CFCs less than 2 decades prior. The Kigali objective is to reduce global HFC use by 80% by 2047. This is a clearly more leisurely timeline and a less ambitious goal than the original Montreal Protocol, which made CFCs fully obsolete in a short time. Kind of makes you wonder, were leaders just tired of making promises after Montreal? Did technocrats advise those leaders to make less ambitious goals in case there weren't strong alternative coolants to replace HFCs? Or did leaders react more excitedly in 1987 because the hole in the ozone layer was a more evident and shocking phenomenon than the usual 2016 conversation about rising temperatures across the globe? Either way, it's early days for the Kigali Amendment, and the effort countries pledge to make should prevent a ½ degree Celsius increase in global temperatures by the end of the 21st century. That is, if we can effectively curb current cooling levels and if we can successfully find substantial alternatives to cooling. If you're interested in learning more about the projects underway to address those challenges, the place to go is UNIDO, or the United Nations Industrial Development Organization. UNIDO has implemented 1,400 projects in technology and chemistry so far, all funded by a multilateral fund called GEF. So far, the projects have made excellent progress, helping to phase out more than 70,000 tons of permanent ozone-depleting substances. If you convert that to annual emissions, that's like reducing 340 million tons of carbon dioxide emissions or keeping 71 million cars off the road. In summer 2020, I had the chance to consult the American Frozen Foods Institute, or AFI, which is a trade group that supports the export of US frozen foods around the world. At the time, AFI was in search of a new focus market for their top members, all of which are household name brands that we've all either eaten or at least seen in the frozen aisle. In our research to find those companies the most promising high-growth entry markets, we discovered the sheer scale of the global food logistics industry and the rising demand for frozen foods in the developing world. Fast food chains, above all, spoke to us as an indication of the global demand for frozen products. KFC, Subway, and McDonald's are some of the most ubiquitous multinationals in the world, with tens of thousands of locations. Those companies' supply chains, as you might imagine, demand a massive amount of ships, planes, and trucks, all with the capabilities to chill food so nothing spoils along the way. One of the greatest contributors to the world's frozen food demand is, again, urbanization. Growing cities bring a lot of promise for climate action through more efficient land use and public transportation. But the rapid influx of people to cities also means that around the world, smaller and smaller proportions of a country's population still live in agricultural communities. This loss of regional farming means that growing city populations, and even those shrinking rural communities themselves, now rely more than ever on food shipped from elsewhere. Most likely coming from the world's last high-productivity agricultural regions. Think wheat grown in the US in the Great Plains, or fruit grown in South America. Those all have to make it all the way to local markets and supermarkets in Japan, Nigeria, Mexico, you name it. The journeys are also likely many hours, if not days, from the source, and that phenomenon exacerbates cold chain shipping and storage needs, which, as we discuss on this show, contributes to climate change through both combustion engines in the ships, trucks, and planes, and through harsh chemical coolants like HFCs. Seeing all the chilled and frozen items that land in our docks, grocery stores, and homes every day, it's no wonder that there's a massive market for keeping things cold the whole way down the supply chain. That's known as the cold chain, and that industry is expected to grow 400% by 2027. The world's fastest growing markets, like China and India, have increased demand for cold chain products by 25% per year for the last 5 years or so. Temple Fennell, the co-founder of Clean Energy Ventures, claims that the cold chain industry has not innovated or addressed blatant emissions problems in over 50 years. So here's how things are cooled. First, producers freeze foods through a process called vapor compression, which has been used for over 150 years. The vapor compression process creates chilled air by compressing a refrigerant such as Freon or CO2, carbon dioxide, into a liquid phase, and then expanding it into a gas phase. When the liquid expands, it becomes colder, and that cold is then blown into the refrigerator or the air conditioner. It's an extremely energy-intensive process that relies on greenhouse gases like carbon dioxide and HFCs, hydrofluorocarbons. Ultra-low temperature cold storage is a common and even more extreme form of cold storage. It generally constitutes temperatures between -40 and -86 degrees Celsius, or -40 to -65 Fahrenheit. It's an important topic of conversation right now because the COVID-19 vaccine, like many pharmaceuticals, requires